So we're talking about number 13. So 13, we are given this original function. The graph is not marked at all. So here's our original f of x. And you have 4 choices, and you're trying to identify which one is correct. So what I just said here is that you must, for the ones that are incorrect, give one clear reason why that could not be the correct derivative. So just find one thing that isn't consistent. For the one that is correct, you must list all of the reasons you can think of for why that is correct, including where does it have x-intercepts, where is it going to be increasing because the original function, where's the derivative going to be positive because the original function is increasing, where's the derivative going to be negative because the original function is decreasing, where is the original function concave up, and that corresponds to where the derivative function is increasing, the degree is going down 1, all of those things. Now, you don't have any markings. It will not get you full credit if you say the correct graph is increasing where it should be, or increasing where the original function is concave up. You must introduce labels and refer to those labels. Okay, this happens a lot on AP questions. You don't have a way of referencing where this interval is, so you must create that way of doing it. So I'm going to call this point maybe A, and this I think is really, the low point is right on the y-axis. So I don't really have to, that I know is x equals 0. And I maybe need this point to be B, and if I want to reference where it's going to change concavity, then I'm going to say maybe right there. I'm going to call the point P, and maybe right here, I'm going to call that x value Q. So I can refer to the concavity. So you could say one reason why, and the correct answer. So for example, graph 1, you could say the original, well, let me do it this way. The original function is a 4th degree. And so f prime should be a 3rd degree. It should be a cubic. You can see that the original function, f, has relative maxima and relative minima at x equals a, 0, and b. So f prime should have x-intercepts at x equals a, 0, and b. Does that make sense? You could say that f is increasing from x less than or equal to a, and from 0 less than or equal to x less than or equal to b. Therefore, f prime should be increasing on those same intervals. So you have to be specific, and then you can go on and do the others. Does that make sense? Yes. Should we talk about concavity or no? Is that okay? Let me just, and so 4, you're going to talk about where it's decreasing. You can add in f is concave up. It looks like from P to Q. So I'll say for P less than x less than Q. And that means that f prime will have to be increasing on that same interval. I have to think about that one. And you can talk about concave down as well. Does that make sense? So just saying that, you know, the derivative has zeros where the original function has relative max and min without referencing them specifically will not get full credit. So you have to be specific. Okay, so for example, you could say on the first graph that the original function should be the original function is increasing for x less than a, which means that the derivative, oh, we didn't say that right, the derivative should be positive. Sorry about that. And it's not. Therefore, we're done with that one. It failed that test. On to the next one. And I think the correct one then is going to be graph 4. Questions? Glad you asked that. Okay. Anything else?
Could you do C and D on number 17, please?
17 C and D. So on 17C, so we have this particle that's moving according to S of t is t cubed minus t squared plus t plus 1. And in C, we want the instantaneous velocity when t is 2. So instantaneous velocity is going to be the derivative evaluated at 2. Because that's what derivative gives us. So the derivative as prime of t, we can use our shortcut power rule on this. So the derivative of t to the third is 3t squared. The derivative of minus t squared is minus 2t. The derivative of t is 1, and the derivative of 1 is 0.
Okay.
And then you're just going to evaluate that at 2. And then it wants units too, so that's going to be 3 times 2 squared minus 2 times 2 plus 1. It's going to be 12 minus 4 plus 1, so that's going to be 9. And our units, it's going to be distance over time, so that's going to be feet per second. Feet per second is our unit. And does that make sense what we're going to do for acceleration now?
Yes, sir.
So you take the second derivative and evaluate that. And that will be feet per second squared. You can either write it as feet per second squared. It's also correct to say feet per second per second. Either of those is acceptable for the units on acceleration. Okay? Anything else on the review?
Can you do number 9?
Number 9. Oh boy, these are helpful. So, on number 9, we are saying that T of H is in degrees Celsius at height in meters. So our T value is in degrees centimeter, and our height is in meters. So what does T prime first of 1200 mean? We're trying to say it in a coherent English sentence, which challenges us all. So remember our units, the input is going to be height. So at 1200 meters, the rate of change of temperature per meter that's what this is going to represent. So it's the rate at which the temperature is changing in degrees per minute when you're 1200 meters up. So we'd expect this to be a positive or negative number.
Positive?
So would we expect the temperature to be increasing as you go up in elevation or decreasing?
Oh, decrease.
Yeah, so we expect a negative number. Is that okay so far?
Yeah.
It gets worse. So what does T inverse of 10 mean? So now remember, we're switching inputs and outputs. So the original we inputted height and got out temperature. So this is now temperature, and we're going to get height. So this is the height in meters at which the temperature is 10 degrees Celsius. So how high have to go before it's 10 degrees Celsius? Okay, now the warm-up. Now, so with the T inverse again, we're inputting a temperature, and so we're going to get rate of change in the meters per degree. So when the temperature is 0 degrees, this represents the rate of change in meters per degree. So what it's saying is how many meters do you go up, or actually how many meters do you go down to increase the temperature by 1, or how many meters do you go up to decrease the temperature by 1. So it's a rate of change in, I have to think about it, meters per degree when the temperature is 0 degrees. Okay. And I have to really be clear in my own mind is what are the units going to be. So what am I inputting? It's the output here. What am I outputting? It's the input here. And it's going to be a change. It's always a rate of change of some kind. So we gotta word it in terms of a rate of change of, so in this case it's going to be meters per degree, which is a strange unit indeed when the temperature is 0 degrees. So words you can use a rate of change, you can say growth, you could say increases or decreases by, and then include your units. Okay, other questions? Okay, so today we're going to talk a lot about stuff we've kind of talked about before, but we'll try to squeeze in maybe some new ideas there, or try to squeeze in a little bit still on this graphing of derivatives, and talk a little bit about the second derivative. So this is, my whole punch is right where the number is. Are we pre-filling that one now? The derivative of powers and polynomials. So we know that the derivative of constant times a function, the constant just hangs out, and you differentiate the function, and then you bring the constant back in. So for example, if we say, what is the derivative of 5x to the third? So the constant 5 is pretty much inert. It just sits there. We use our power rule on x to the third to get the 3x squared, and then we multiply that result by the 5 and get 15x to the second. That make sense? We know the derivative of the sum of two functions. I'm going to say plus or minus g of x. We're just going to take the derivatives of each one and add or subtract the results. So we got prime of x, and then whatever the plus or minus was, g prime of x. So we can differentiate these crazy polynomials. So if we say f of x is, let's say 4x to the 7th minus pi x squared plus, say, 1 over x minus, say, 4 times the square root of x to, let's go 4th root of x to the third, plus maybe x minus the square root of e, then we know how to take that derivative. Don't we? Maybe that's aspirational. Okay, you ready? Derivative of 4x to the 7th is 28x to the 6th. Good. Is that making sense? I mean, not the head. Okay, derivative of minus pi x squared is minus 2 pi x. We're thinking of 1 over x as x to the negative 1 for derivative purposes, so its derivative is going to be Good. Negative x to the negative 2, just using our power rule. Is that okay? Derivative of, we're going to think of the fourth root of x to the third as x to the 3/4. So the derivative of a minus 4 x to the 3/4 is going to be, nice, exactly, minus 3x to the negative 1/4. This always throws people when you're starting out. The derivative of x is 1. And the derivative of the negative square root of e is 0, because that's just a constant. Okay? Okay. So we can see also these things we've been talking about, you know, where is the function not differentiable? We can see that for these various strange powers. So if we have f of x equals x to the 3/5, we have g of x is equal to x to the, what do I want to call that, to the, we'll say 3/4, and h of x is equal to, say, the square root of x, and let's even make one just crazy, j of x is equal to x to the e power. So no matter what the power is, we use our power rule. So a prime of x is 3/5 x to the negative 2/5 power. And that's fine, we're done. But just remember, we could write that just to clarify why this has the derivative that it does. So we get something like that. And so you can see then that at 0, what this is going to do is, as you approach 0 from the left, then plugging in a negative number gets squared first, it becomes positive. The fifth root is going to still be positive. So if we take something very, very small, then you have a positive over something very, very small and positive, it's going to go to positive infinity on the left. With me? Katie? Yes. Just looking for some kind of nonverbal feedback there. As we approach 0 from the right, plugging in a small positive value, again it gets squared, stays positive. Fifth root is still very small, positive over very small positive. You can see that our vertical tangents give us this kind of graph. So what we may be asked to do on, say, a test question, say Friday, is if we have a curve that is going to have a vertical tangent, and we're trying to, this is our f of x, then to graph its derivative, f prime of x, we could see that, cut it off there a little bit. So it looks like there the derivative is maybe not quite 0, just a little bit negative. So it's not a corner point or anything, so I'm not going to make that an open circle. I'm just going to start it as a little bit negative there. As we approach this vertical tangent, it's going to get steeper and steeper, bigger and bigger negative slope, until it falls off the cliff and goes to negative infinity. So it's going to dive and go there. On the other side is still that vertical line, and now it is still a very, very steep negative, gradually leveling out till it's not quite to 0, still a little bit negative. So it's going to come up and do something like that, still below the x-axis there because it's still a little bit negative. So the graph of a vertical tangent is going to result in a vertical asymptote in the derivative where they go to the same infinity. That's the takeaway. So g prime of x, when we have x to the 3/4, oh, I didn't want that, scratch that. Let me do instead 4/5. I want to go even over odd. So odd over odd, the whole thing less than 1 is going to be a vertical tangent. And here we're going to get 4/5 x to the negative 1/5 when we subtract 1, which would be fine if all I wanted was the derivative. I'm going to write that as 4 over 5 times the 5th root of x. Okay? So as x approaches 0 from the left, I put in a very small negative. 5th root of the negative is defined and stays negative. You're going to get a positive number over something very, very small and negative. It's going to go to negative infinity. So in the graph of this thing that has a cusp, it's going to, the derivative is going to fall off the cliff and approach negative infinity on one side. Is that okay? On the other side, as we approach 0 from the right, I put in a small positive. Its 5th root is still small and positive. Positive divided by a very small positive goes to positive infinity. And so in this graph, it's going to do something like that. So cusps will have derivatives. The derivative of a cusp is going to have a vertical asymptote and go to different infinities. Okay, so if I gave you, say, on a test question Friday, something that looks like, say, here's the original, and can you draw the graph of the derivative? So this is f of x, and we're going to try to graph f prime of x. So it looks like over here, maybe that's just either 0 or just a little bit positive. So I'm going to put just a point down in there. As we move towards the cusp, it's getting steeper and steeper, but positive slope until it's going to go off the cliff to positive infinity. On the other side, off the cliff, really big negative. We're going to weigh to a little bit negative. So it's going to do something like that. So the derivative will be a vertical asymptote, where they go to different infinities on each side. I'm going to stop there. I don't think those are as important. I want to get on to talking a little bit about increasing, decreasing from the first derivative, concave up, concave down from the second derivative. So let's say first f of x is x squared, and let's consider f prime of x and find intervals where the original graph f is increasing and decreasing, and then we'll consider f double prime of x and find intervals where the original function is concave up, concave down. And we know what y equals x squared looks like, but let's see what the calculus tells us. So f prime of x is going to be what? 2x. So we want to know where is the derivative positive, where is the derivative negative. That's going to give us information about where the original function is increasing or decreasing. So I'm going to set it equal to 0 because that's where it can change from one sign to another. And that's going to be at 0. So I'm going to do a number line. There is f prime. It's 0 at 0. And if we plug in numbers to the left of 0 into 2x, the derivative, is that going to be positive or negative? Negative. And numbers to the right, positive. So we have that f prime of x is less than 0 for x less than 0.
Wait, Mr. Street, why is it negative on the left and positive on the right?
So if we plug into the derivative a negative number, say negative 1, 2 times negative 1 is negative 2, that's going to be a negative number. So the derivative is negative.
Okay,
See how we're doing that?
yes, sir.
So when the derivative is negative, this means that the original function is increasing. And on increasing and decreasing, we do include the endpoints. So it will increase, negative, sorry. I really messed you up. The derivative is negative. Therefore, the original function is decreasing because the slopes of the tangent lines are negative over there. For x less than or equal to 0, we include the 0. With me? Okay.
What are the arrows mean again? Increasing or decreasing?
So f of x is decreasing for x less than or equal to 0. It's a parabola. So we know a parabola looks like this. There's y equals x squared. Okay, so we said its derivative, slopes of the tangent lines are all negative to the left and right.
Okay, I get
The
it.
original function then is falling from left to right on those arrows.
I know you're talking about 2x, sometimes confused.
Okay, so we're using 2x to talk about where it's going to be increasing, decreasing.
Okay.
Okay? Let me get the other part. I'm really racing the clock here. So let's talk about f double prime. F double prime of x. So the second derivative is going to be 2. Now, where is that equal to 0? Never. But it's positive. So the second derivative being positive means the original function is going to be concave up. If the second derivative is negative, it's going to be concave down. So what we get then is that f is concave up from negative infinity to positive infinity, or you could say for all reals, because the second derivative is always positive 2. Does that make sense? Intervals where the function is concave up and concave down are always open. Never include the endpoints. Increasing, decreasing, always include the endpoints unless the function is not defined at that endpoint. Maybe it's a vertical asymptote or something like that. Okay? Boy, this goes too fast. All right. Well, so much more we can do. If you get stuck, there's some support videos that can help. Because I didn't get anything done that I wanted.